Hello, everyone, and welcome to Physics 212. This is Lab 6 on projectile motion. So projectile motion is essentially motion of a projectile, right? An object that's being launched, usually at some angle, although it could be horizontally above, at a certain height above the ground. And it's the motion of the object when it's just in the vicinity of the Earth's surface, right? Under the influence of gravity. And as usual, we're going to ignore the force due to the drag force, the air resistance force. We're going to assume that's negligible. Okay, so what I want to do first, let me move to the iPad just to give you an overview, remind you of projectile motion. Okay, so let's say we have an object launched at some particular height. I'll draw like a coordinate system in here. So the horizontal line is like the table. Let's say this is the object. And we'll assume it has some initial velocity. So this is like the launch velocity, V naught. And it makes an angle with respect to the horizontal. So I'm going to call this the launch angle theta. Okay, and we know from experience what this object is going to do, right? It's going to leave this position. It's going to rise, I'm doing green here, rise to a peak, and then it's going to fall back down to the ground, something like that. Okay, so usually what we do first is typically you want to find the components, the x and y components of that initial launch velocity. So to do that, I can simply go to the tip of the velocity vector arrow, right, and project onto the x-axis. So I'll project down onto the x-axis. So this component right here, this horizontal component, that would be v naught x, right? It's the horizontal component of that initial launch velocity. And then to find the y component, I project the vector onto the y-axis. So this component right here, this vertical component, that would be v naught y. And they're easy to find, right? Since this is a right triangle, if you know this launch angle theta, then you can find the x component by taking the magnitude of the velocity. So that would be v naught without a vector on it, right? The length of that arrow, basically, which is the speed, also called the launch speed. If you take that and you multiply by the cosine of theta, that'll give you v naught x. And if I take v naught and I multiply by the sine of theta, that'll be v naught y. Okay, now let's consider, let's talk about the x direction first. So if we assume that there's no air resistance, then once the ball leaves the launcher, we're really only interested in after it leaves the launcher, right? When it's in the air. Once it leaves the launcher, there are no forces acting on the ball or the object once it leaves the launcher, no forces acting on it in the x direction. So if there's no forces acting on the ball in the x direction, that means, you guys will learn this when you talk about Newton's second law, that means that the acceleration in the x direction is 0. If the acceleration in the x direction is 0, what does that mean about the velocity in the x direction? Well, it must be constant, right? 0 acceleration means constant velocity. So at least in the x direction, if I look at any point on this path, the x velocity is going to be the same. So I'm going to draw it the same length that I drew v naught x. I'm going to make it the same length here. Even at the peak, it'll be the same length. So this is in the x direction. And right before it hits. Okay, now what about the y direction? Well, again, we're going to ignore air resistance, but we do have forces acting on the ball in the y direction, right? In fact, we have the gravitational force, which is the weight of the object, the weight of the ball. So that means there's an acceleration in the y direction, and we know that this acceleration, we already know what it is, right? It's going to be g, or if we're being careful, negative g. So the object is undergoing an acceleration, right? Constant acceleration. So in the y direction, it has this free rise, free fall motion. So initially, right, we had this large positive vertical velocity, the initial velocity in the y direction. And then a little bit time later, it's going to be still positive, but smaller, right? Smaller magnitude. Then it'll be still positive, but smaller. At the peak here, actually in the y direction, there's no velocity, right? It's instantaneously zero in the y direction. In fact, it's all in the x. Then after the peak, it'll be small, but negative, right? In the y direction. Then larger, and so on, and larger. So you can think of projectile motion as consisting of two motions: constant velocity motion in the x direction and free rise, free fall motion in the y direction. If you put those two together, you get the motion of a projectile. Now, there's another quantity that often comes up that's going to be very important. So if you look at this distance from, basically it's an x displacement from when it's launched to when it hits the ground here, right? That's sort of a horizontal displacement. Well, it turns out there's a very special horizontal displacement that's defined to be from the point of projection, so right here, because it was launched at some height, to a point on the path that's at the same elevation as the point of projection, which is right here. So I'll do this in blue. So this distance from here all the way to here, right, when it's at the same height, this is called the range. So that's the range of a projectile. Now we're going to be computing the range, and it turns out that the theoretical formula for range, it depends on several factors. So usually we call range R. It depends on, and sort of makes sense, how fast the ball is being launched at, right? So that launch speed, the magnitude of the launch velocity. In fact, it's V naught squared. It depends on the launch angle. And the factor is the sine of 2 times the launch angle. And it also depends on how strong gravity is, right? It depends on the acceleration to gravity. So we divide all this by G. So that's the formula for range. It's the launch speed squared times sine of 2 times the launch angle, all divided by G. Now notice it depends on what units we're using. In most of the lab, we're going to be using CGS units. And that means G here, the acceleration of gravity, is going to be 980 centimeters per second squared. But later when we look at the simulation, G is going to be 9.8 meters per second squared, because in that case, the simulation uses SI units. And then of course, the velocity also has to be in the correct unit. So in CGS units, velocity would be centimeters per second, and SI units would be meters per second. And that means the range is going to come out in either centimeters, which is CGS units, or meters, which is SI units. Okay, so that's sort of the general description of a projectile launched at some particular angle. Now, the special case that we want to look at is when a projectile is launched horizontally. This is like the first part of the lab. So let me discuss that a little bit. So here, we're going to have our projectile. Now it's launched at 0 degrees, right? So it's launched horizontally. This would be V naught. And we know, again, we know the motion. Immediately, once it leaves the gun, gravity is going to start acting on it, and immediately it's going to start to fall, right? So it'll be something like this. And it'll hit the ground over here somewhere. Okay, and this is, let's say this is a height h above the ground. So actually the coordinates of this point right here would be like, let's say this is 0 in the x direction. So this would be like 0 comma h, right where it's launched. And then this point right here, let's call this distance. So this is a horizontal displacement. I'm going to call it x. I think I use x in my handout. So this is like x comma 0. Now, what if we want to find the position of this object at any time? Like, what is the position at some time and I want to find the X and Y coordinates of that projectile at that particular time. Okay, so let's say I want to find the X position, the Y position for any time, and I know that the object is launched horizontally. Well, we can actually derive those equations, right? We know that we have constant acceleration. So for let's do the X direction first. So in general, right, X, think of this as like the final position is equal to, you know this from your constant acceleration formulas, right? Your kinematic formulas. So the final position X is equal to the initial position X plus the initial velocity in the X direction times, we'll assume it's starting, the initial time is 0. So this is like delta T is just T to make it easier, plus 1/2 AX T squared. Right? Again, that's just one of your constant acceleration formulas. So we can simplify this because we know that this projectile is starting at initial position in the X direction of 0. So that's 0. We know the initial velocity in the X direction. It's all in the X. So I'm just going to call this V naught X. I'll call it V naught, right? The entire velocity is in the X direction times T. And because there's no forces acting on, or no air resistance, there's no forces acting on the particle in the X direction, then the acceleration in the X direction is 0. So this simplifies to X is equal to V naught T. And in fact, you can think of this X, this position, as a function of time, right? For any time, if I plug in T and I know the initial launch velocity, that'll give me the position in the X direction. Okay, so that gives you this value right here for any time. Now for the Y, we can do something similar, right? We can argue, well, we know in general, it's got to have this general form, Y is equal to Y naught plus V naught YT plus 1/2 AY T squared. And again, we can simplify this. What is the initial position in the Y direction? What is this Y naught? Well, if you look at this, right, it's got to be H, right? Because it starts at a height H. So this is going to be H. What is the initial velocity in the Y direction? Well, it's all in the X, right? There's no velocity in the Y. So this is 0. And then what is the acceleration in the Y direction? Well, we know that that is negative 9.8 or negative 980, depending on what unit. So that's negative, I'll just call it G, negative G, T squared. So this formula is going to simplify to Y is equal to H minus 1/2 GT squared. And again, you can think of this as a function of time. So this is the Y position for any function of, for any time T. Okay, so, and actually there's a question from the lab manual, question 5, that asks you to sketch the motion when a projectile is launched horizontally. So it's going to look pretty much like that, right? Like our sketch here. And then also asks you for the equation that gives the X and Y positions as a function of time. So you can just, now that we derive them, you can just give these two equations. This is question 5. All right, now there's one more thing we can get out of this. If you think about it, right? When the object leaves the gun, so at time 0, and then when it hits the ground, right, this time here, that time is really the time of flight of the object, right? It's the time that the object is in the air. So from when it leaves the gun to when it hits the surface is the time of flight. Well, we can calculate that using our formula that we just found for the Y position. Because when it hits, right, when the object hits the ground here, or hits the lab bench in our case, what is the Y position, right, when it hits? Well, it's got to be Y is equal to 0. So if I plug in, right, if I go to this equation and I plug in 0 for Y, and I solve this for T. So basically you can move that negative term to the right-hand side. So this is equal to h, right? Multiply everything by 2. Here, I'll do it here. So I'm going to get gt squared is equal to 2h, right? And multiply both sides by 2. So 2 times 1/2 is 1, that cancels. And then the other side, 2 times h is 2h. Then I would divide by g, right? So that cancels. And then finally take the square root of both sides. And you're going to get t is equal to the square root of 2h over g. So this is another way of really of calculating that time, but that time is simply the time of flight of the ball. So this is the time of flight. So this is going to be important. We're going to use that formula in the lab itself. Okay, so let me go back to the handout. Okay, so we talked about the general case of a projectile at some angle. We talked about the special case where it's launched horizontally, where the angle basically is 0 degrees. We're going to need this later, so we came up with the formula for the range of a projectile. And then we also found when it's launched horizontally, that special case where it's launched horizontally at 0 degrees, we found the x and y position as a function of time. We found an equation for both the x and y positions, right? And we did that here. Remember, x is v naught t, and then the y was h minus 1/2 gt squared. And the reason why we needed this is we wanted to find the time of flight of the ball, right? Time of flight of the object. So when we set h equal to 0, that's when it hits, and solve for t, that must be the time of flight. And we found that the time of flight is the square root of 2h over g. And again, just to review, remember, 2 important characteristics of a projectile are the fact that the horizontal motion is constant, and the vertical motion is like free rise, free fall motion, right? If you put those together, you get the motion of a projectile. Okay, so that's the review. Now for the experiment, there's several parts here. So for the first part of the experiment, basically what we did was we launched a marble off a table, off the lab bench, horizontally. So it was launched horizontally. And then based on that information, you want to answer the first 3 questions from the lab manual based on the fact that the marble is launched horizontally. So question 1 was simply, sketch a picture of the motion that you have observed. Question 2, why does the ball immediately start to fall instead of just going straight? And question 3, are there any external forces acting on the ball to account for the motion that you have observed? And you want to ignore air resistance. And if there are forces, give the direction of the forces. Okay. And again, we're only interested when the ball is in the air. Don't think about the force due to the launcher. That's only, so the launcher certainly applies a force to the ball, but only when it's giving it its initial velocity. As soon as it loses contact with the launcher, then there's no more force due to the launcher, right? And we're only interested in after it loses contact with the launcher, just when the ball's in the air. That's the motion that we're interested in. Okay, and again, if you miss this lab, you can talk to your lab partners about this. The second part is similar, but now we're launching 2 balls at the same time. And one of the balls is simply going to drop down. So it has no initial velocity in the x direction. It just drops straight down, accelerates downward. And the other one is launched horizontally with some initial velocity. And the question is, if they leave the launcher at the same time, so one drops, one is launched horizontally, which ball hits the ground first? Okay, and again, you can talk to your lab partners because they would have done this experiment and listened carefully to see which ball hit first. This question too, if you ever watched Mythbusters, they did one episode where they shot a gun, like shot a bullet and dropped a bullet at the same time. And the question was, which bullet hit first? The one that's just simply dropped from rest, or the one that shot out horizontally at some initial velocity, in fact, a high velocity if it's shot from a gun. And if you understand that, then that will give you the answer to this question, question 4. Okay, then we get into the wooden launcher. And again, the first part of the lab is the ball, the black marble is launched horizontally. To get an idea of what how the data was collected, I did create a couple of short videos, right? One where the ball is launched horizontally. You want to make sure you watch those videos. And then the other one where it's launched at an angle onto the landing platform. But this part is where it's launched horizontally. So basically, we did 5 launches, right, of the ball horizontally. And we measured the height of the gun from the landing platform. So it's basically the height from the top of the landing platform to the bottom of the gun. And basically, you can just record this once. So this should be the same value for all 5. We're going to assume it's the same for all 5. So then you want to find the average, which is going to be that value, whatever the value is, right? Because it's the same for all 5, right? That'll be in centimeters. Again, if you need this data, get it from your lab partners. If for some reason you can't get it from your lab partners, contact me and I can give you some data for this. Okay, the second measurement that we made for each of these trials is we measured the horizontal displacement from the edge of the gun. This is like the X displacement from the edge of the gun to where the ball landed. And we knew where the ball landed because we had a piece of carbon paper there. So we could record the location. It left a mark and we record the location of the ball. So we found the horizontal distance from the edge of the gun to where it landed. So again, 5 trials, and you want to calculate the average here. And then using a timer, we triggered the time. So when the ball leaves the gun horizontally, it triggers the timer. And when it hits the landing platform, it shuts off the timer. So that difference in time must be the time of flight, right? The time that the ball was in the air. So we measure that directly using a photo gate and then a landing platform. So that information is here. Again, 5 trials. And you want to average these. That's going to be your average time of flight. Okay, question 5 was simply, it's what I mentioned earlier. You simply want to, it says, draw a set of coordinate axes and draw a picture of the motion of the marble when it's launched horizontally. Label the coordinates of the initial and final positions of the marble, and then write down the 2 equations that we derived that give the X and Y coordinates of the marble as a function of time. So actually, I give you those 2 equations here. We derive them. You could just write these 2 equations down again. And in your picture for this should look very similar to this, right? When it's launched horizontally at 0 degrees. Okay, so that's all. Question 5. We kind of did it. I just want you to make sure you understand that. Question 6. You're asked to determine the time of flight of the ball using the equation that we derived. Okay, so we measure time of flight a couple of different ways, right? We measure it by measuring it directly with the photo gate and the landing platform. We have the average time of flight here. But in this case, I want you to calculate it using the information that we got from that formula, right? From kinematics. So really all we need is the height of the gun. So you can take your average height of the gun here, times 2, divide by 980, because we're in CGS units, so G is 980, and then take the square root. That's going to be the time of flight. Okay, so that'll go on the table here, that time of flight. And now that we know the time of flight of the ball, we can calculate the velocity, the horizontal velocity, which is V naught, that the ball left the gun at. It's simply going to be the displacement, right, which is the X average that you got in your table here. So you can take that average divided by this time of flight, divided by the time you got from question 6. And that will be the velocity of the ball when it leaves the gun, right? And we know that it has to be true because it's the horizontal velocity of the ball. In this case, we're just launching it horizontally. This is that special case. And this is going to be what we're going to call our predicted or accepted velocity, this calculation from question 7. Okay, and make sure you show me all these calculations, right? Whenever there's calculations, make sure you show me the calculations. Question 8, another way of determining the velocity is using the CPO timer and the other photo gate. Again, if you missed this lab, ask your lab partner about this. And this is similar to what we did when we did the ball drop experiment. To get the velocity, I could take the diameter of the ball, which is 1.90 centimeters, and then divide it by the time. So your lab partners would have recorded this value right here. So you can get this value, the time it takes that diameter of the ball to pass through the photo gate. So if I do 1.90 divided by the time, that's going to be another estimate of the velocity of the ball when it leaves the launcher, the marble, the gun. Okay. This we're going to consider to be our experimental velocity. So the velocity from question 7 is your accepted or predicted velocity. The velocity from question 8 is your experimental velocity. It's kind of arbitrary, but we're going to use those two terms. And hopefully they're fairly close. So what I want you to do, the rest of question 8 here, is I want you to compare the two velocities. So again, the predicted velocity, this comes from question 7. The experimental velocity comes from here, from question 8, from this table. That'll be the same value, question 8. So compare them by computing a percent experimental error. Now, remember, you always divide by the predicted, the one that we're calling predicted. Okay, then question 9, we're basically computing the horizontal displacement two different ways. One way is calculating it, right? We know velocity is displacement divided by time. So if I rearrange that formula, I can say the displacement, which I'm calling capital X, is velocity times time. So the question is, what velocity, what time do I use here, right? Because we calculated it several different ways. So what I want you to use for the velocity here is the experimental velocity from question 8. So this is going to be your experimental velocity from question 8. And the time here is going to be your time of flight from the table. So it's going to be the average right here, the average time of flight from the table. Okay, so if you multiply the velocity from question 8, experimental velocity, times your average time of flight from the table, that should give you a good estimate of the horizontal displacement, X. And that is what we're going to call the predicted horizontal displacement. I call it distance here, but it's really a horizontal displacement. So this X here is the predicted horizontal displacement from this calculation. Velocity from question 8 times time of flight, average time of flight from the table. And then the other way, the way that we can get experimental horizontal displacement is simply from the table, right? We have the average from this table. So the experimental horizontal displacement, you're just going to use this average here. So it's two different ways of computing the horizontal displacement, or that distance. And now you want to compare them. So compare these two, hopefully they're fairly close, by computing a percent experimental error. So again, remember, you subtract, take the absolute value, make it positive, and divide by the predicted. We're calling this one, the one you calculated, the predicted. The experimental is just the average from the table. And hopefully you get a fairly small error here. Okay, next part. Here, and this is sort of like the main part of the lab. Again, you need to watch my little video lecture that I made on how we actually collected data using the equipment. This is where we use the gun, right? The wooden guns with the marbles. And we launch the marble at these particular angles. So 15 degrees, 25, 35, all the way up to 75. We already know at 0 degrees, the range is 0, and 90 degrees, the range is 0. I have a landing platform that's at the same height as the gun itself, the edge of the gun. So therefore, when the ball hits the landing platform and I have a piece of carbon paper with a piece of white paper, so it leaves a mark, I can measure the distance with a tape measure from the edge of the gun to where it leaves the mark, and that's going to be the range. Right? Remember, the range is the horizontal displacement when it's at the same height, from the point of projection to a point on the path that's at the same elevation, same height. That's going to be the range. So we're going to do 3 trials for each particular angle, right? And again, if you don't have this data, get this data from your lab partners or contact me and I can give you some data. Okay, first question is you're going to find, you're simply going to calculate so you want to fill in this table and then calculate the average of the 3 trials. So for each of these angles, just find the average range. Question 10, now using Pascal Capstone, you're going to plot range, so meaning average range versus angle. So range is on the y-axis and angle is on the x-axis. Okay, so range on the y versus angle on the x. And when you do that plot, you want to do a sine fit. So the curve is a sine function. So you want to do a sine fit, and then you want to answer these questions from question 10 in your lab manual. It's basically asking you to find the optimal angle that the projectile was launched at and the angle at which it occurred. And then the maximum range. So actually, let me jump on the iPad for a second to explain this part, and then I'll show you how to actually get these values from the Pascal capstone graph. Okay, so actually we're plotting range this is in centimeters on the y-axis versus angle degrees on the x-axis. We already know when the angle is 0 degrees, the range is 0, and when it's 90, it's 0. So basically it's saying if I launch it exactly at 0 degrees horizontally, then immediately it starts to fall, right? It never gets back to that same location, so that range must be 0. If I launch it at 90 degrees straight up, then the ball is going to go up, come back down, and then again, that horizontal displacement, that range will be 0. You guys may know this, when, like theoretically, when should, like for what angle should the range be maximum theoretically if you ignore air resistance? You may know this, it should be around 45 degrees, right? So your data might look something like this. Let's say it won't be exact, but let's say it looks something like this. You want to do a sign fit to the data. So let's say it looks like that. And then to answer these questions, so question basically 10 and 11, you have to find the peak of your graph, which is, and you really want the peak of the fit, right? The curve that you fit. You can use something called the coordinate tool. I'll get on Pascal capstone in a second and explain how to do this. Basically what it does is it gives you the coordinates of that bullseye there, of that point that you picked. So it's given you the X and Y coordinates, which in this case is really the angle and the range, right? So it's given you this value. This is like your range. So this would be your, I'll call it R max, maximum range experimental, because it's coming from the graph. And then it's giving you this value. This is like your theta. We're going to call this the optimal angle. So I'll say theta optimal experimental. So it's the maximum range experimental and it's the angle at which it occurred at. Okay, so let me remind you how to graph that and how to find those two values there. So you go to Pascal capstone, right? We do our usual classic templates. We're going to choose this one with the table and then the graph. So for the x-axis, create new user entered data, I want angle. And for the units, you can either type out degrees, or you could use, if you hold the Alt key down and you do 2, 4, 8 and a numpad, it'll give you a degree symbol. Or you can just write degrees to be fine as well. And then for the Y, we want range, right? This is really your average range, and units are going to be centimeters. Okay, so let's say I'll use the same values for the angle. So 0, 15, 25, 35, 45, 55, 65, 75, 90. And then for the range, of course, this is 0. Then let's say you got 60 centimeters at 15 degrees. Let's say your average was 98 at 25 degrees, and then say 116, then 128, then 115, then 95, and then 59, and then 0. Let's say those are your values. Kind of just made these up, but so on the x-axis, we're going to plot angle. On the y, we're going to plot range. And then for the title here, you can just put range versus angle, right? It's always y versus x, so range versus angle. You want to do the usual, get rid of the line segment connections by hovering over a data point, right click, and then uncheck show connecting lines. And then for the fit, again, here's where you want to do a signed fit. So that's this one right here, sign. and actually does a pretty nice job, right? So it does a good, if you have decent data, it should do a nice job fitting the data. Now we want to find the peak of the graph here. We don't want to find your like highest data point. We actually want to find the peak of the curve with the sign fit here. So this point right here. So how do I find that point? That's where we use the coordinate tool. So to do that, you have to click on the coordinate tool, which is to the right of the fitting tool, right here. And we're going to choose add coordinates, the first one. And then we need to change one setting. So we're going to click on this, right click, go to tool properties, and we want to go to coordinates and see where it says snap to pixel distance is 100. That means when it gets close to one of your data points, it wants to jump to the data point. If it's within 100 pixels, jumping to the data point. We don't want it to jump to the data point. So we want to decrease this. Let's move this all the way down to 1. So we'll make that 1. Hit OK. And now if I move this around, oh, let me recenter that. If I move this, I can find the peak of the curve. Like right, say right there is the peak of my graph, okay? And then these values, this is the coordinates, right? But remember, this is really the x, which is the angle. So that would be like the angle at which my maximum range occurred at. And then this 126.21, that's going to be my maximum range for my data that I made up. So then you would just hover over the border here, right click, copy display, and then paste this into your lab report, and it'll keep these values right in the graph, right? You want to make sure you have these values because you're going to need these values to answer those questions 10 and 11. Right, so basically that's all there is to it. You're going to do a sign fit, then use that coordinate tool to actually find the peak of your graph here. Okay, let me go back to the handout. Okay, so question 10 again was to create that graph, right? Range versus angle. And then you want to compare the optimal angle experimental, which is from that coordinate tool, right? Whatever value you got, 40, I forgot what we got, 44.90 or something degrees. Compare that to the optimal angle theory. And this is 45, so you can just write 45 here, right? We're going to assume theoretically it should be 45 degrees. So compare those angles by computing a percent experimental error. Again, the 45 is going to be your predicted accepted value. So when you compute the percent error, remember you subtract, make it positive, and divide by the predicted or theoretical one. Divide by the 45 times 100. That's your error. Then question 11 is similar, but now you're going to compare the max ranges. So the experimental max range, that comes from the graph, from that coordinate tool, right? That R value, when you found the peak, that's going to be your max range experimental. Now, what is max range theory? Well, we can calculate it. We can calculate it by using this formula. So remember, the formula in general is V0 squared times sine of 2 theta divided by G. But when you plug in 45 degrees, because theoretically 45 should be the optimal angle, when you plug in 45 degrees, you have 2 times 45, which is 90, and sine of 90 is 1. That's why I don't have sine of 2 times 45 here, because it's just equal to 1. So to find this value, you're going to calculate, you're going to use your launch velocity. What I would do is use the launch velocity from question, because we calculated it twice, right? I would use the launch velocity that you got in question 8. So your experimental launch velocity, square it, and then divide by G, which is 980. And that will be your maximum range theory. And you'll know that you did this right, because it should be fairly close to what you got experimentally. Okay, and then finally, compare these two by computing a percent experimental error. So again, when you divide by the theory one, right? This divide by this one, but this is your accepted predicted theoretical value. And hopefully they're fairly close, these values. Make sure you show me all these calculations, right? Show me this calculation, show me the calculation for the error. Same thing here, show me the calculation for the percent experimental error. All right, and then finally, the last part is very similar, except now we're going to do basically this range experiment again, but we're going to do it using the simulation. So you want to go to the simulation. I'll show you to you in a second. You're going to this is SI units now, right? So you're going to set the initial speed, the V naught of the launcher is going to be 18 meters per second. And then you want to launch it at these angles, at 25 degrees, 30, 35, 40, all the way up to 65 degrees. And then you're going to use a tape measure to measure the range for each of those angles. Okay, so I have a table here. So for each of these angles, you're going to measure the range, right? So let me show you this. Let me go to the simulation right now. Okay, so here is the PHET simulation for the projectile motion. You're going to click on it. There's several options. We're just going to use the intro. And a couple of things. You want to bring this, the cannon down so it's launching from 0 meters, not at 10. So we're going to bring it down to 0. By the way, this part is like where it actually launches from, right where the X is. So it comes out of here. And then we want to put the initial speed to be 18. So you can use this slider here, or you can just increment it to 18 meters per second. That'll be the initial launch speed that it launches at. And in the angle, you're going to go from 25, 30, 40, all the way up to 65 degrees, right? Those angles. Now, for the object, it doesn't really matter what you use as an object. Pumpkin is fine because we're going to ignore air resistance. I'll just put cannonball, but you can launch whatever you want. To launch it, use this red button here. So it'll launch it and it hits the ground, right? So remember, it's launching from the ground, it's hitting the ground. So this horizontal displacement is actually the range. Well, how do we measure that? Use this tape measure here. So if I drag this down, this is the beginning part of the tape measure. So I want that right at the X of the cannon, or it leaves from. And then the other piece I can pull out to where it landed, right there. And I can record that distance, so 25.44 meters. That'd be my range for 25 degrees. Then I would increase this to 30 degrees and launch it. And then I can just drag this, right, because the other end is staying at the cannon. And then measure that value and so on. And obviously 45 should give you the greatest range. You can measure that, and then it should be symmetrical, right? When you do 50, that should be similar to the same, really, it should be the same. We did exactly as 40, and then 55 should be the same as 35 and so on. Now, if you have so mine, everything fits on the screen. If you have a screen where it goes off the screen, you can always zoom out or zoom in. Okay, so if you have to, you might have to zoom out, and then it'll scale everything so that when you bring this to the correct point, it'll give you the correct measurement here. I know some computer screens, it goes off the screen, so you have to zoom out. In this case, I was able to just do it directly. Okay, so collect all that data. Let me go back to, all right, so I'm back at the handout. So you're gonna fill in this data table with those range values that you measured, right? Again, now we're in SI units, so this is meters. Then the questions, and I just started labeling them at 1 because this is different. It doesn't come from the lab manual. This is part of the simulation. So you want to answer these questions though, but they're very similar to what the other questions that you previously answered from the lab manual. I want you to plot range versus angle again using Pascal capstone. Fit it with a sine wave, use the coordinate tool to find the maximum range experimental and the angle which it occurred at. Then compare, just like we did before, compare your optimal angle experimental to the theoretical optimal angle, which is 45 degrees by computing a percent experimental error. And then compare the max ranges. So compare your max range experimental. This comes from your graph, right, from the coordinate tool. And in theory, you have to calculate by using V naught squared over G. But be careful now, V naught is 18 because we set it to be 18 meters per second, and G is 9.8 because it's SI units. So this is 18 squared divided by 9.8. That'll give you max range theory. And then compare these two by computing a percent experimental error. Again, divide by the theory one. This is like your accepted predicted one. Okay, and you should find that this value is very small, right? It's a simulation, so it should give you very, very good data. And then the last question, I just want you to kind of play around a little bit with the simulation. So it says, using the simulation, set the bullseye target to 20 meters from the base of the cannon, keep the height of the cannon at 0 meters, with the angle of 25 degrees, what speed should the cannonball be fired at to hit exactly the center of the bullseye? Now change the angle to 45 degrees and determine the correct speed to hit exactly at the bullseye. So you're just going to record these values, and you don't have to show any work or anything. Just record the values that you got from the simulation. So let me show you that quickly. If you go back to the simulation, by the way, if you want to clear out the simulation, you can just hit this reboot button here, this orange button, and change it. So you want this still at 0. Now we want to move this target to 20 meters. And the first angle is 25 degrees. And you're just kind of playing around with this to guess, to see. Let's say you think, I don't know, maybe 24 meters a second. That should hit it. Let me try that. Nope, that's way too fast. Okay, I'm launching a pumpkin right now. Then you decrease, let's go to like, say 9. You think 9. Nope, that's way too short. Eventually, you're going to find exactly the correct speed, so you hit right in the center of the bullseye. So I just want you to find the correct speed. You could calculate this, right, using the range formula, but you don't need to do that. I just want you to experimentally find it by playing around with the simulation, and then do the same thing at 45 degrees. Well, let's say you think it's 10. No, that's not enough, right? So it's getting more than 10. And if you go too far, that's too much. Okay, so again, you should find the exact speed, the launch velocity, so that 45 degrees, it hits right at the bullseye target, which is 20 meters away. Okay, and that's it. You're just going to record those two values. Okay, so now we're back at the lab manual, lab handout, and then you're done. There's nothing else after that. So it sounds like a long lab, but it's not too bad. But you want to make sure when you do your group lab reports that you include all the data, you have 2 graphs, right, that you want to include for this particular lab, and you want to show me all the calculations, right, for theoretical ranges, for percent errors. Show me all the calculations wherever there's a calculation. All right, great, thanks.